Okay, cool. Today we have Dr. Andrew Putnam. I am lucky enough to have him as one of my very good friends who I get to see ideally multiple times a week. So welcome, Andrew. I'll do a little bit of like intro for folks, but I actually didn't know most of this stuff about you. So that's a bad friend moment. I guess we don't talk about the nitty gritties of like things you've worked on at work all the time, but we keep it high level. So yeah, I mean, Gemini did a really good job finding all the things about you on the internet. I will share with you the deep research report that it came up with. Very interesting things. So welcome, Andrew. For
Thank
those
you.
who are listening, we have this network of folks around the world. There's about 200 and change of us, and it's the people who build the things that we use every day. There's no one more behind the scenes getting shit done over the last 15 years or 20 years than you. I try to think about it and abstract it for people. I'm like, yeah, it's like Andrew. He works in like silicon hardware, architecture, design. I bet like most of the things you've done on the internet over the last 20 years has flowed through stuff that he's right. Like his electrons have powered things on the internet or in work. So I thought today would be a good day to kind of sit down and make up for all the bad friend moments of asking you these details as a friend, but also for others to learn from. So I always love to just kind of say, like, you know, Andrew, like, what was little Andrew like? Where did he come from? How did he become the nerd that decided he wanted to go to university? And how did what was that path and journey? What did that look
Yeah, well, first of all, thanks for the kind intro. I'm glad, really glad to be here. I'm also glad that the internet knows that there's an Andrew Putnam that is not the professional golfer. I actually used to compete with a couple of Andrew Putnams around the world for clicks, but then once that guy won his first PGA tour, yeah, you have to go to about page three of of the search engine results to find my page.
nice?
Um, but at least I'm a solid number two up there. Um, Yeah, so I grew up in Colorado. Was the Both my parents were school teachers. My dad was eighth grade math teacher. Mom did math for education, and you know had a great time through the public school system. Went to University of San Diego. Actually got a triple major in physics, electrical engineering, and computer science. I guess maybe I couldn't decide what I wanted to do. Um, and then while I was in school, I also worked full time for Raytheon, so did some things for ship self defense system and things in that regard. Actually, yeah, that was all full time too while I was in school. And then I came up to University of Washington, got my master's and PhD in computer science and engineering up there. And then after that, hopped across the water to Microsoft Research. And I think I've always been kind of at this boundary of hardware and software. I think a lot of that came from have had got my first Apple IIe when I was maybe 3 years old, and then always had computers that were just not quite good enough. And you always had those friends who had games that could run because they had better computers, and it was the trick to figure out how could I make my little 486 25 megahertz machine run these games like Star Control 2 or something like that my buddy's Pentium was running with no trouble. And so you just learned all kinds of tricks of EMM 386 and HighMem.sys and how do you deal with all the different kinds of ways to do that. And that really took a level of understanding of both the hardware and the software, really low level things. And I guess I just always kind of gravitated towards that. So when it was in school, it was like, well, I already know how to do a lot of that stuff because I lived the nitty gritty. Um, and so it's really been a pleasure kind of all the way through to just bounce. And I think best way to describe myself is if I'm hanging out with software people, I'm definitely a hardware guy. But if I'm hanging out with hardware people, I'm a software guy. And I think that's often where you find a lot of the best work is finding those boundaries.
Nice. Okay, so random question. How would you explain to people our age, and people who are younger, the turbo button on the
the term,
PCs, on the old PCs? Tell us how
yeah,
that was supposed to work and if it did work.
So I think the turbo button was supposed to increase your clock frequency and make it actually work. There was always a good question about why would you ever not run it on turbo, which was a really, really legitimate question. The crazy thing is I found that out a few times because there were some games that were timed to the processor clock, and I don't know if that was just sloppy programming or what they had to do, but if you started the game and it was on turbo, suddenly the enemies came at you at like some crazy pace, and then you needed to like unclick the turbo button so that the game would go at the right, at the right speed. So I think there were a handful of legitimate reasons, but for the most part, people just put that button on the cases of computers, especially like way after anything ever supported turbo. They just put it on there so you could feel like you're like, yeah, my computer's so fast it's running in turbo.
I
Um,
remember like it always had an orange light, which I found interesting, or a yellow light, which is
yeah,
weird.
it's because it's supposed to give you this level of like caution and fear. It's like
Yeah,
press this button, but be cautious.
no one ever explained like to a normal kid who's just playing like Rebel Assault and Doom and stuff, like what I was supposed to do. But it was interesting to be like I think every kid was like, it's gonna make your computer like burn up. Like it's gonna like, no, I don't think it's going to. But um okay, so when you were young, you were like a typical the rest of us, video games nerds, building computers. Um Went to university, kind of took all the core sciences there. Um, when you decided to come up to Washington and do your post grad, um, how did you define yourself in this world of like hardware architecture and silicon?
Yeah, well, the funny thing is actually of my three majors, I was the worst at computer science, and so that's what I decided to like go get my PhD in. Because I was like, oh, I'll get better at that. And so I ended up kind of there, but as usual, like once I got into the software, software department with all those programmers, I gravitate as much towards the hardware as possible. Um, Grad school can be kind of eye-opening sometimes because I think a lot of folks who end up there are used to being at the top of their class. And then when you get, that many people who are used to being, the top student or, at least top few, by rough definition, okay, not strictly statistical, but like half of you have to be below average.
Yeah, yeah,
And
that's
I think
fair.
that's really where you kind of learn that, people start to get really specialized, in one area. And I think in many ways you push to become the best in a particular area, but also that often kind of creates a bit of a silo where it makes it harder to break out and and find the new things. And so I think by being a little bit out of place in a software department, being a hardware group, I could continue to kind of cross those boundaries. UW is also really good there, in terms of how much collaboration they have across departments and a lot of the different initiatives they have, like the Science Institute or things like that, where they encourage you to work with other departments and collaborate in interesting ways. So yeah, I think that really helped. Got a great education, education doing that. Um,
Did you
and
find then that transition to MSR was like just double down on that same thing where now everyone's like the smartest person?
Yeah, yeah.
Yeah.
MSR, Microsoft Research, is one of the most amazing places in the world. It's a industrial research lab, but it very much encourages academic collaboration. I think one of the best things that happened early in my career is I got to work with a bunch of people who were Turing Award winners, like absolute pillars of the field. Chuck Thacker, um, Burton Smith, and other just huge luminaries in the field, Rick Rashid, Doug Berger, who are really at the cutting edge and understood where the world fit with research and industry and product teams. A lot of these folks lived in the DEC Research Lab, Xerox PARC, AT&T, and Bell Labs. And I think what they found is um, that there isn't kind of an industry or product versus research, that there's always going to be this balance between doing some kind of pure academic research and then finding a way to turn that into perhaps product, and maybe not. Maybe the point is just advancing the field, and MSR has really been really good at a lot of that, where they don't try to direct your research towards something that is guaranteed to be used by the product groups. They kind of rely on the product groups to do their own advanced research there. They're really looking for what are the things that Microsoft or the product groups aren't looking for. Where can we really jump in front and even steer the field in a new direction. And so a lot of the work that I ended up doing around hardware acceleration and specialized computing was way early, especially in the advent of the cloud, and not the kind of thing that the product teams would have done themselves. But we definitely are standing on the shoulders of some giants who created the kind of culture and and framework with which we could do this kind of development work and really move the needle in a new way that wouldn't have been driven by standard kind of industry business product processes and procedures.
Yeah, I mean, great way to kind of, the next thing I wanted to dive into is a great segue, which is, we were at Microsoft at the same time, didn't know each other. You're in the building with all the super smart people, and I'm over there building Windows and stuff. But a great example of, we were on two sides of two different like engineering stacks and two different roadmaps. But in a time where we were still PC, tablet, mobile era, trying to figure that out. Your guys are over there figuring out this thing called search is big and Bing is a thing at Microsoft, and we're a little bit behind on cloud. And I don't even think we just started calling it cloud at the time, right? So kind of walk us through like Project Catapult, which I think is publicly named. Uh, kind of, how did you're sort of young in your career, coming over, you're working on things. How did that come to be? Can you tell us what it was, what the mission was? Again, great example of, as we're over here trying to figure out what a phone is and a tablet is, there's a group of people in research saying, hey, the next set of requirements of computing are X. We need to go figure out like what that looks like. Love to learn more about. That was your big moonshot number one that you worked on, I think.
Yeah, so it was actually a project that the product teams came to us with at first. So it was Bing who came. They had just been renamed. I think you remember they were MSN search, then live search, and they had
Windows
gone through
Live
quite a
Search.
few Windows Live. So there were quite a few iterations, and they had just kind of rebranded themselves as Bing. And they came in and said, Google is obviously way ahead in the space. Like, is there anything you folks in research can do to help us like catch up and figure out a new way forward? And we're like, okay, well, I mean, we're the kind of the computer architecture and systems research team. Mostly what we do is make stuff go fast. So let's go take a look at what you have and see what we could possibly make go faster. And at the time, they were running the pinnacle of machine learning models. Because if you think of most search engines, like they're really just giant machine learning models. And so it's kind of a funny like intro to that was AI before AI was the cool thing. They were running boosted decision tree forests. And when we first started our interaction, it took about five like milliseconds to run through about half a second to run through a decision tree forest. And we're like, well, if we did that in hardware, we could run that much, much faster. And so I put together kind of a proposal and said, okay, well, we could build this really quickly, but obviously we can't build a chip, a custom chip for this. That's not going to make sense, right away. But we could do this and we could prototype it on things called FPGAs, field programmable gate arrays, and we could really make this work. And so got together, putting together the architecture, put together kind of a prototype. But there was also an eye-opening piece to me, which was like, okay, well, I've come up with this great hardware. It's much faster. And then it turns out just a few months later, they had gone from essentially, 5,000 microseconds to about 250 microseconds. You're like, oh, the software evolved very quickly.
Yeah.
And then, I improved the hardware as well, but instead of, 1,000x faster, 2,000x faster, it was, 50, 60x faster. And then the software evolved again and again. And you realize, wow, like even if you come up with the very best hardware architecture, like this software is going to continue to evolve. And so we got really deep into how do we co-design this hardware and software so it can evolve separately, but not have to constantly change every time each side moved. And that became a great collaboration between MSR, Doug Berger's team. Doug Berger and I kind of started that one, and Siddharam Blanca over in Bing. And we basically put together a set of different features and just iterated and iterated and iterated and came up with something where the whole of Bing could run about 2x faster.
Mhm.
But my favorite part of that collaboration was that because the software kept evolving, what was an awesome thing and what was something that was shippable one day, maybe a month or two later, was no longer shippable. It didn't do, it wasn't fast enough, or the software had changed enough. And so one day I went to the office where it turns out that this boosted decision tree forest stuff was so fast that a new bottleneck had emerged called freeform expression. So I went to my friend's office and Bing, Kyle Hollahan, who was there, and I said, "Hey, buddy, like your part is now the slowest, component in Bing. Could you teach me a little bit more about it? I'll see if I can come up with some kind of design that'll work." And this was on a Thursday, I remember. And he was like, "Yeah, sure, not a problem. I'll send you whatever you want. But I'm kind of busy tonight. Do you mind if I get it to you Monday?" And I was like, "Yeah, dude, not a problem. Don't want to cramp your style too much." That guy went on a, Red Bull and Mountain Dew, pizza fueled like hackathon of his own. And then on Monday, instead of sending me, all of these design docs or the code, he wrote a giant email. It's like, "I've improved the performance of my piece by like 1,000x." You're like, dude, well, that's both awesome for you, but like terrible for me because I'm supposed to be making you an accelerator. And in the end, Siddharam came to me and said, "Don't you worry, Andrew. Even if you never ship a single thing to production, you've had an enormous influence on the performance and relevance of Bing by basically running around and shaming all of these developers into improving their performance." Um, and so I think that was also a huge lesson for me, where it's not necessarily about whether or not you ship your hardware or whether or not you're successful. It's whether or not the end-to-end product is successful and the various ways in which you do that. And I think especially when it comes to accelerators, when it comes to cloud computing, these applications are constantly evolving. They're going to continue to evolve, and the only thing that's going to keep you relevant for more than a handful of weeks, months, years is your ability to adapt to these changes at the speed of software. And I think we learned a lot of lessons, and really appreciate Bing and the opportunities that they gave us and the collaboration we had with them that taught us just how to do that at a software pace using hardware.
Amazing. Yeah. It also, like, on the other side of it, the power of being in the office and going to someone's door and saying, "Dude, can you just, like, what's going on?" This idea, like the serendipitous moment, right? Like that spark, huge on ROI for company, product, customer, et cetera, right? This idea of
Enormous.
like multidisciplinary conversations and like connection and just getting people around a whiteboard, pulling people out and having a discussion. Like, look at the
Yeah.
result.
One amazing example that I had from that was, as I said, we had these Turing Award winners wandering around MSR all the time. And suddenly one of the functions that we had to put into our accelerator was natural log, which is not super friendly to hardware. And we were on my dry erase board coming up with how we were going to do this. And Burton Smith, one of the fathers of supercomputing, walked by my office like, "You hear natural log?" So actually, way back in the day on the CM5, I was dealing with the same problem. And I came up with this, and he like basically off the top of his head came up with this natural log approximation circuit that they had done when they were building things out of basically discrete components almost. And you're like, like you just did this? He's like, "Yeah, yeah." I'm like, if you hadn't have been walking by my office at that moment, like this never would have happened. And it was it was a massive change. And basically, we went from, it was going to be about 28 clock cycles to get this thing done. We were able to do it in 7 to 11, depending on the thing. And it was just an enormous performance boost that just couldn't have happened if you didn't have a bit of this serendipitous interaction between people who weren't even technically in the same group, or just people who shared the same office. And so I think when you mix talents and have these kind of cross collaboration, you never know what problems are going to get solved that otherwise could have taken weeks, months, or even sunk programs.
Yeah. I mean, even for myself, like for me, it was disciplinary, right? Like this engineering PM, kind of working in Windows of a CS background, I get dumped into a design world. What? Like they don't speak my language, they don't use my tools, but we all have the same goal, which is like make this thing work best for the customer. And the hybrid of that changed my career forever, right? Like, oh, realize there's a half of my brain I wasn't using. That is the half I like to use, right? But then you start meeting these people who have just decades and decades of wisdom. Right? Just, hey, by the way, we did that 10 years ago. And the learning from that was this. And maybe you just want to apply that. Like, yeah, I mean, this is the benefit of working at a place like Microsoft. It's been around for what, 50 years?
Yeah. And I think especially when you talk computer hardware, things like that, the amount of stuff that wasn't done 10 years ago, but was done like 30, 40 years ago. Incredible stuff from IBM, Xerox, from companies that you don't even think would have done there, but they had constraints way beyond many of the constraints we have now. And
It'll,
I've actually
it'll,
found one of the weirdest uses of AI is like sometimes it can go back in time and find some of these things that you just wouldn't be able to find otherwise.
yeah, I have this, the tangent of another conversation, but this deep down desire, if like ever came back to Microsoft, I'd want to be the librarian, right? It'd be me, a set of people, multidisciplinary people, and a bunch of agents just continuously taking all the stuff that Microsoft did, think about all the files and decks and of ideas I have somewhere sitting in a drive somewhere in that organization and like bringing that to the next 25-year-old person who's thinking about a problem saying, hey, like the smartest people have been thinking about this for the last 30 years. We need a way to tap into it. Great use of AI. On that note, so we're solving problems for Bing, search, cloud is a thing. You make your way from optimizing things in that world over into the world of Azure, right?
Yeah.
Tell us
So
about how that kind of career shift as well from, you're not just research anymore, you're building product.
yeah, so that was interesting because at the time Bing was the biggest dog in the data center by a long shot, and we first started our collaboration with them. But then there was this little startup group that was having a bit of success called Azure. It was kind of also called Red Dog way back in the day, and that's a fascinating story if you ever listen to Mark Russinovich and at all on exactly what Red Dog was from. What became pretty clear is that even if we were wildly successful with Bing, which kind of we got to the point where, I mean, a 2x improvement in end to end in a cloud workload is borderline impossible because of Amdahl's law. But even if we were that successful with Bing, it probably wasn't going to be a huge success unless it could also work for Azure, because while Bing was bigger, Azure's growth trajectory was pretty clear. And so we had to come up with something that was going to work for Azure. And what really was pretty amazing is we were able to take the exact same hardware and transform it from walking boosted decision tree forests and doing feature extraction to doing software defined networking. And so depending on what image you loaded on this exact same piece of hardware, it would go from, something that would be basically be doing AI processing to something that would translate all of your network packets running through a network. Because obviously, when you put two VMs in the cloud, they think their IP addresses are 10.1.1.1 and
Yeah.
10.1.1.2. But really, one is in Boydton, Virginia, and another
Yeah.
is in South Africa, and it's got some crazy amount of policy and other things around. And so what we did is we took all of that processing that was done on the CPUs and we offloaded it to the FPGAs. And then even the like customer software didn't have to be aware of this. It would just send the packets, and then the FPGA would intercept it. It's what we call the bump in the wire topology. It would grab the packet and then do all the transformations. And then on the receiving end, it would basically grab that packet, undo them all, and then hand it up. And so that was kind of what we came up with to do that. That's when I made my transition. As that was going out, uh, it was clear that we needed kind of to do a little bit more work to integrate that in with Azure, do the same kind of things we had done with Bing. But that was going to be harder to do there from just within MSR. So I thought I would be jumping over to Azure networking at the time for, maybe a year, maybe 2 years. MSR has this thing they call the golden ticket, which is if you go to the product groups, you could basically come back to your old slot, even if they don't have a slot for you. They'd let you, go try to push your research into production. So I jumped over, started working with Daniel Firestone, Albert Greenberg and Dave Maltz over in Azure networking, and we launched what became accelerated networking. And that was a massive performance improvement. It was the fastest networking in the cloud by a long shot. We did it. And saved a ton of power. It was also weirdly in a way that we hadn't expected, became a solution to a lot of the problems around Spectre and Meltdown, these security
Mm.
problems, because those basically targeted times when the hypervisor, basically elevated privilege, operating system would kick in. Um, and because we didn't do that, we just allowed the packets to send in user mode, to the FPGA. We didn't have to worry about those transitions on every network packet. And so it was basically a huge performance benefit to one of the biggest cloud security problems that had been, that the cloud had ever seen. And so that was kind of this, again, we're adapting and doing a new function that we never designed the hardware to do and never expected to need to do. And it was just really neat that we were able to kind of make that work out and solve new problems with the same hardware. Um, since that, we've continued to evolve. I went from 40 gig to 50 gig to 100 to 200 gig, 400 gig, and now a lot of that we've added just feature after feature. It's now publicly called Azure Boost, but we've added a bunch of storage acceleration to it. We've added all kinds of diagnostics, telemetry. We continue to evolve every day. One of the funny things that we hear all the time is, okay, well, why are you still deploying on FPGAs? Why are you
Yeah.
still using these things that I describe as silicon Legos? It's like, well, you make a Lego design because you don't know what you want, but now that you've made it, like, why don't we go ahead and make it a real ASIC?
Yeah.
And I think a lot of that is that even in the storage and networking spaces, the number of things we want to do, the rest of the software ecosystem, the number of requirements that come on continue to change and continue to change. And everybody thinks, if there's been one constant across the entire program, it's been that everybody thinks that now, things have changed a lot in the past, but now they're going to be stable.
Yeah. Oh, look at
Um,
that.
and
Yeah.
then every time about a year later, it's like, no, it turns out there's a whole bunch of new stuff we need to do. Um, and I think my favorite analogy there came from Mark Hill, this legendary computer science professor at Wisconsin, who came and worked with us at MSR one time, and then he basically said, I finally get why, Andrew, why you like these FPGAs so much and why you like flexibility so much. Because I was thinking when I was 20, I thought I had my life figured out. But then I look at myself at 30. It's like, how did your 20-year-old self do? And you're like, okay, that was embarrassing. I thought I knew what I was doing, but now I'm 30. I've graduated. I have my first job. I know where I'm going in my career. And then you turn 40, and you're like, so how'd your 30-year-old? Okay, that was embarrassing. But now that I'm 40, I have a house. I have a couple of kids. I know exactly what I'm doing. And then you turn 50, and you're like, okay, I was way off when I was 40, but now I'm 50. I know where everything's going. He says, I turned 60 and I look at my 50-year-old self and still didn't know. He's like, and I just turned 65 and I look at my 60-year-old self and still didn't get it right. But that doesn't stop me from looking at myself at 65 and saying, but now I know where the world's going, what the future is. And so I think it is funny to find this, to find this desire to optimize and say, okay, well, I think we know everything we're doing. Now's the time to bake it into silicon. Now's the time to harden everything. And now we're in an era where everybody says, we don't know where the future is. We don't know where AI is going. There's so much, everything's evolving so fast, but we should bake it in because I definitely know where the future's going. And so for me, I just, continue to think, no, it's going to continue to be a time to have flexibility, to, try to be able to adapt, wherever the winds take us with the most flexible hardware, and basically find the right place to put things in software, in hardware, wherever it needs to go.
I love it. It's a great, like, just adding on top of that, like, let's talk a little bit more about the AI stuff that's going on, right? Like, the concept of modularity and being, I mean, this is agile in hardware at the lowest level. Like, this is what this is. This is what you're talking about. And in one world, you're seeing PR in hardware, which is, oh, we're building a chip that does this. And you're like, Is it a chip? Is it, like it's a lot of PR stuff. But like, as you think about, to your analogy, like, look where we are now with AI. We're on, day one, or day two, maybe day three. Give us a little bit of thought on how that, how you think, and as much as you can, like, but more about the architecture, how it's evolving. Um, on one end, there's like this quantum thing you guys are doing, and that's like out there working backwards almost. And now you're moving forward with this AI that's just adding more variability, because we're still trying to figure out what the hell we're going to use it for, and how we're going to scale it, and power, and networking, and all those other things. Like, this is your daily job. I get to hang out with you all the time and see just all the variables changing. You know, for other people listening, like, how do you think about those variables? How do you like use them as a strategy? And how does that fit inside the Microsoft picture? A lot, but like, what's on your brain right now, and how you juggling all these balls?
Yeah. Well, I mean, one way I always look at it is going back to Bing and thinking, what actually we've been playing with this AI machine learning, path for quite some time. Instead, it was only like 10 years ago that the pinnacle of machine learning was boosted decision tree forests, and then came kind of deep neural nets and CNNs, and then we made an accelerator for that, and then there was LSTMs, RNNs, and so we made an accelerator for that. And then it was graph neural networks, and now it's like transformers. And so one of the things you always worry about is when you see these chip startups or things that they're trying to target, a particular thing, the space just evolves so quickly that it's very hard for hardware to keep up with that kind of evolution. And you see that the one architecture that's really done the best by a long shot is GPU, which is even more general purpose in many ways than the FPGA. And so the flexibility that that's offered has massively outdone any of the low level performance, or any of the things that hardware people care about on their spec sheets. Your clocks, your clock speed, your memory size, your speed and speed. None of that's mattered compared to the algorithmic development that the GPUs and the flexibility that they give you have allowed, in terms of evolving the space and really making things fly. And so I think that, that shows, how much more flexibility can do more than anything. There's also a piece where right now, what people care about and what the market cares about is, where are the next features going? What can I do now that I couldn't do yesterday? They're not really focused heavily on, how do I do it for a little bit cheaper, a little bit faster, the kinds of things that we care about in the hardware space. And so when you spend most of your time trying to perfect something while the world just moves around you, it ends up not mattering. And even if you do manage to get it, let's say you got a 15% reduction in power, nobody really cares, because they're not going to think, wow, I did that same thing I did yesterday, but with 15% less power. It's, what can I do new today that I couldn't have done yesterday? And until the field stops evolving at the pace it's at, it's going to be really hard, I think, for hardware people to lead the charge into a new era, because it's the algorithms and, the features, the ingestion of data that's really at the forefront of what's changing things now. That said, for people who think that transformers are now the pinnacle and it's not going to change, like, bad news, it is. It's definitely not going to be that. And I think you just have to look to nature for inspiration. Doug Berger, a mentor of mine in a big way, always likes to point out, it's like, wow, all this power that we throw at, the cat recognition photos or something like that. It's like a fruit fly can do that at essentially, nanowatts of power and do it better. And so clearly it's not just a small gap between what's possible and what we're doing today. We don't need to build megawatt data centers to do things if, a fruit fly or a cockroach can figure it out, on, a couple of grams of, tossed out apple.
Yeah.
And so I think there is just this enormous space where we're going to have to explore, we're going to have to figure it out. One of the things that gets interesting, though, is, what they call the hardware lottery, which is essentially, if researchers can do their work on hardware, on a particular kind of hardware that's available, they tend to actually constrain their research to what works on that hardware. And so in some ways, it's a virtuous cycle for the GPUs, because they get all of these workloads. There's all of this thought, there's all of these people who are really focused on machine learning in a common platform, even a common software ecosystem for the most part with NVIDIA and CUDA and that. And so they can all really make a ton of progress. But it tends to keep the entire research field a bit funneled in that one direction of what works well on GPU. I think um, what you don't want to do is allow only focus in that one area. And so I think we need to be able to give hardware capabilities, fast speeds and feeds, and things, but allow exploration in directions that are not exactly where the GPU is, at its best, which is SIMD computation, vectors, things like that. And so a lot of the best work that we've done in this space has been around, well, what are some new features, things that you couldn't just throw into a GPU that we could possibly exploit in FPGA? A lot of the best work, some of my friends like Eric Chung and Beta and Adrian Caulfield knows, they developed all of these different network protocols for super fast RDMA in the background and different numeric precisions. So they called MSFP, became MXFP, this kind of standard about like low bit width floating point numbers, things like that. Those have later been adopted and kind of superseded by FP4, but those were hugely influential in many of the AI chips. But those are all developed on the FPGA because it gave us that platform where we could try it out. You didn't have to simulate it in software, so you could run real full speed, AI algorithms, but get hardware level performance out of it. Um, and I think there's still an enormous place for that kind of development here. And then obviously, the more you go to energy constrained environments or something, you've got yet another big playing field. So the GPUs are amazing. I stand in awe of what they've accomplished. But I still think that there's an enormous amount of room um, for other more unique kind of hardware architectures to play. And I think this kind of programmable hardware and FPGAs is a really promising place to allow people to figure that out, but still have that level of hardware performance that makes it real, so they can run real applications.
Yeah. Um, yeah, there's so much there. I'm gonna clip that later so everyone could just like reuse that over and over again when they're thinking about their roadmaps. But on my side, I care about like once things I'm on the other side of the cycle. Okay. So how does the architecture and just the fundamental theoretical math structure, what does that mean for on the edge? What does that mean for super low power, for robotics, for automation, for all these other things? We haven't, that's always the tail end of like innovators trying to say like, look, there's really good theoretical and application at the big data center level, but how we move information between MCUs on arm of a robot is interesting too as well, right? Or in assisted living, or in medical devices, or robotics, or manufacturing, or space, and all those other things. It's like, hey, there's for every NVIDIA GPU, there's a Nordic Semiconductor little low power chip, right? The delta between these two things is like, we need to start also moving some of those downwind, because that's the application layer, right? Where we're going to have the big compute. How are we going to move bits around the world, like the photonics, all that stuff, right? But at the end of the day, where we're really bullish is like, okay, how do we apply this stuff in the physical world, right? And in doing so, I don't know if there's enough people thinking about it. It's like, how many people are actually thinking about this? And there's going to be some level of, okay, we can compute things, but how are we applying things? I don't know. What's your take on, I think that's the next 15-year gap as well, as we think about as kids come through the funnel and researchers come through the funnel, we are over indexing on the LLM world for a little, because we're still trying to figure out what is it good for? How do we turn it into, like, how do we turn this science into tools? Right. And what are the modern tools? And then on the other end, either you parallelize or you have to, you put these in order, saying, no, we have to figure that first out before we figure out the application there. I think there's just really interesting bifurcation happening in the innovation
Yeah.
space.
Well, and some of it is driven by AI, but some of it I would argue is just about specializing the hardware. So much of the world basically runs on just software that we already have written and finding new ways to reuse that. And I think if you look at how pervasive software has become, it's obviously enormous, but at the heart of it, it's generally still the venerated old CPU core. And even there, it's really just a handful. Maybe it's x86, but for the most part, it's ARM. And that's because of the software ecosystems, not because somebody couldn't figure out, a better, slightly more efficient chip, but the fact that it doesn't matter on the chip level if you have to spend an enormous amount of time and energy and effort developing new software, then all of those savings are basically going to disappear. So it was better to go with something really general purpose, try to augment that, reuse the software stack and get it out the door than it was to make something hyper specialized. When it comes to AI, I think people feel like we can reopen the doors to, well, this is important, it's AI, let's reopen the door to specialized hardware, doing something new. But if you have to completely redo the software stack, you're going to find yourselves in much the same areas as anybody else in embedded systems, where the difficulty of trying to attack the entire stack and develop that from scratch just gets really difficult. And so then, what are the abstractions we can have where we can reuse a lot of the software from other parts of the stack without having to redo everything ourselves? The thing is, CPUs are actually pretty interchangeable, and we have an enormous amount of tooling, compilers, runtimes, assemblers, libraries that allow like nice reuse of code that was written by an intern, from 20 years ago, possibly even yours. Like, it's really easy to use that code on, a CPU that's not even out today. It'll still run. When it comes to specialized hardware, getting stuff to run on a Vertex, from a Vertex 6 to a Vertex 7 was an incalculable task for us early in the program. So even the same company's products, like just one generation newer, and it was a complete redo. And so when you start with that in the specialized hardware world, you just don't have that layer to build upon. So you're constantly refighting old battles that you'd already won. And in the GPU space, you see kind of a middle ground here where, each new GPU generation, they actually spend a bunch of time in the tools, especially like CUDA, trying to help you make that transition. But it is a much more painful transition than it is from your, Gen 6 Intel processor to a Gen 7 Intel processor. In fact, I would guess almost nobody listening to this podcast knows what generation processor they have in their laptop.
Not anymore.
But people definitely know what generation GPU they're on for the most part if they're GPU developers. And then if you work in specialized hardware, it matters massively if you're on, one version versus another, and maybe even, one that's the same generation but a slightly different configuration. It's completely different. And so if you can't figure out how to make things more common, I think that's really going to hold back progress in this space, because you don't want to have to, just because you're in an energy constrained environment, you don't have to completely rewrite the software stack and then start losing out on the innovations that are coming from other parts of the ecosystem. And so again, that comes down to, we've got to figure out how to explore, but it's not the metrics by which we will be judged are not really the standard hardware metrics that you see on data sheets. It's going to be, how well does this thing work? How quickly can we get it out the door?
What's the impact?
And that's
ROI?
really hard for hardware folks to understand, because they really want to see, speeds, memories, power. And it's so hard for them to say features and flexibility, because they just don't have the metrics to talk about that. But those are going to be the things that determine their success.
Yeah, it's super interesting, right? Like x86 ARM, now we have, Qualcomm's got to figure out what they're doing on the edge side, and hey, well, they need a CUDA for that, right? And then we have the GPUs, and they're trying to figure out some consolidation there, but really just a dominant player in the space. The hardware software integration, that lowest level, but great use case for AI, right? Hey, you go figure out the things translate this into the new platform at some level. It's a great way to accelerate the gap, maybe, or the switch over. But at the end of the day, it's you need to, at some point, get everyone on one platform, right? ARM is the new thing, but that took how long? To really get it into any developer can then translate their thing, or this sensor company can make it for ARM and x86 or whatever it is. That's 20 years. more.
It's constantly evolving. And now that they're trying to support more accelerators that you can attach to ARM and trying to keep the libraries, together, that becomes a massive undertaking. RISC-V has kind of jumped up as, a new way to do that. But again, part of it is that they don't have as much legacy to support. Once you kind of build on this legacy of supporting all this old software, it becomes harder and harder to change things and adopt new hardware constructs. But again, the power of reusing the software. I mean, why is NVIDIA dominant now in this space? Why hasn't AMD been able to make a bigger dent in the AI, hardware race? And they're definitely making some good dents, but NVIDIA and ATI, which AMD acquired later, they have been neck and neck on raw GPU performance, raw hardware specs, for a couple of decades now.
Yeah, early 90s, right? Like
Right.
late 80s. Yeah.
So what's so different? Like, why isn't AMD, this $4 trillion stock as well? And, generally this comes down to, it's not that it's better hardware, it's that there's a better ecosystem and more people on that ecosystem called CUDA. But CUDA even undersells it, because CUDA is shorthand for all of the software that goes on it. But that's not a compiler, it's not a language. Any more than saying, like, you can't say, okay, well, my CPU runs C and his CPU runs C, so that means they're the same. You're like, no, like, that is not at all what this is about. It's about the libraries, the assemblers, the tools, the profilers, the debuggers, things that make people and developers more productive and get you to that end target. And that's where NVIDIA has really shined. And so I think when I see hardware startups, or I see these pitches about, this chunk of silicon that's going to be, 10x more efficient than an NVIDIA. I've even seen one that's like 600x better than an NVIDIA and something else. It's like, well, the thing is, if AMD with their GPUs has not been able to kind of bridge that gap between, we have the same hardware, the same fundamental, fundamental execution environment and thing, they haven't been able to bridge that gap. If you're a startup with a new chunk of silicon that's non-GPU, not only do you have to bridge that gap between CUDA and non-CUDA, you have to bridge that gap between GPU and
And
whatever kind of new
yeah,
architecture you're doing. And that's a major hardware problem as well as a software problem. And I would argue that that's actually maybe even a harder problem. And so unless you are either laser focused on a particular vertical or particular space, or you think you're going to somehow out-resource NVIDIA, it's a very, very difficult place to be, even if by some cool hardware metrics you're really successful. Just think of there's 4 trillion of opportunity easily for AMD if they could just solve that CUDA problem. Now you're trying to not only solve that one, but an additional one that's easily as hard. That's a tough place to be unless you're either going to go after something very different, very specialized, or just find some other way in which you can be successful, to really
it's a
move the
great it's
needle and push things in your
a great job
direction.
application, right?
Oh yeah,
License your design and IP, but you're in the wrong execution pathway. I mean, you nailed, like, I come from the consumer other side, right? Which is, yeah, I mean, this is what Microsoft got right first and early, right? At scale in the 90s, right? It's like, developers, focus on the developer platform, build from developers backwards, build from PC up, right? The Wintel, yeah, but they owned everything in between, right? And then on the mobile side, Apple's like, hey, let's consolidate, let's make it like, great, we have a silicon that runs our platform, blah, 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 etc. Right? And like, we'll do the tooling from cloud to
yeah.
you can
Well,
kind of say that it happened in the web as well, and like all these other things. But in the world of this AI side of things, which I think we've bucketed it too much into like this one thing. But if you don't have the development stack for something, okay,
yeah. In the end, we're all out to please a customer, an end customer. And I often think it's very, very hard to lead from the bottom of the stack, to lead with hardware, because in the end, the customer is rarely paying for hardware, and in general, they don't care. I think in our era, like at Microsoft, we tried to lead from the bottom by having the best OS, and we changed the OS from Windows 7 to Windows 8. And we're like, well, they're going to love it once people learn how to use the touch interface. I actually remember this conversation I had
I
with
was
some of the PMs on Windows
yeah,
8.
I was a part of that hot mess, especially
Yeah.
as a person who was responsible to making it more touchable, which was an over index on that for Windows 8. But yes,
Yeah. But it turns out that like people don't want to learn their operating system. They like their applications. They want their stuff to just run. And I think that's a big difference from, well, what if we give them, hardware that's going to be better, what's going to be faster? And in fact, not only do customers not care that much, but what do developers tend to do if they have two pieces of hardware that operate differently? The very first thing they do is they make abstraction layers
yes,
to make the software work the same.
yeah,
And so I've seen this over and over where somebody makes this piece of hardware and they're like, okay, well, we did this thing and it saves like it makes the clock frequency on the block ramps 2.5% higher. And you're like, the very first thing we do is we make an abstraction layer that now takes 2 cycles to do every operation instead of 1, so that it works the same. And
yeah,
so you improved the frequency by 2.5x, and then we doubled the number of clocks it takes. So in fact, you're actually 90% or 90% worse than you were before. And that happens in the software space monumentally. Um, to the point where you often see just huge amounts of abstraction layers in there. So even if you do make these hardware changes, if it's not, fully optimized all the way up and down the stack, software people make abstraction layers, which makes the hardware improvements, masked at every layer. And so it's just a tough place to be to try to lead from the bottom unless you're going to really think all the way up the stack and figure out, okay, what is the customer in the end going to see? What are they going to care about?
I love it. Okay, we have a few minutes left because I know you have a busy day re-architecting
Always.
the cloud and making bits move around the world. If you weren't doing this right now as your job and career and passion, what would you be doing?
Well, that's tough. The funny thing is, no matter what I do, I've had a lot of fun doing it. My first high school job was actually janitor. Like I was
Oh, really?
maintenance at a waterfall tourist attraction called Seven Falls in Colorado Springs. Um, and had to empty trash cans and clean toilets and thing. And like you just find all these efficiencies you can have and all these different ways to have fun. I had the best time doing that. I ended up like taking over the computer systems too. So, that was super cool. And then even as part of all the work I do here, it's like you do a lot of development, a lot of architecture, too many PowerPoints, but a lot of what made this program successful was that we were mostly grad students who had just come into Microsoft. And yes, we were talking to these giants, but even they took time each day to do development, to do building. And so we always took care of our own labs. We always brought up our own systems. And I personally have been in the factories in, China, Taiwan over and over. I've spent more time on the factory floor than almost anybody I know. In fact, one of the best compliments I've ever had is from some factory workers in Tianjin, China, who pointed to me and said, "That guy works really hard." I'm like, these guys are 996, like working overtime all the time, and they think I'm nuts because I kept working through lunch. Um, and I think when you do like when you get into things and get your hands dirty, you really understand up and down the stack what it takes and how your decisions influence the rest of the stack. Um, to the point where um, one of my interview questions has now kind of become, okay, if you're going to come to Microsoft, we famously pledged to do, be carbon neutral by 2030. What are you going to do as a hardware engineer or a software engineer to help Microsoft hit that? And for the most part, people say things like, I'll turn off the lights and I'll recycle and things like, okay, so sure. But like, what's different? What are you going to do? And they often think, well, I don't know. What can I do? I'm just a software engineer. I'm just a hardware engineer. It's like, think of the impact you can actually have,
Yep.
because what do people end up doing? What do they care about with their computer hardware? What it runs? If they can make it last a little bit longer, then you've actually had a much bigger environmental impact because they didn't throw away their laptop a year early or 2 years early and buy a new model. If they were happy with it for 2 years, you've had a massive impact. And you think of Microsoft as a company with the operating system, the tools we have that allows so many applications to run across so many different devices, so many different things, that if we can make it last a little bit longer, you avoid all that embodied carbon, avoid all of that, all of that unnecessary waste. And in the world of specialized hardware, that's going to become a much, much, much harder problem because CPUs, again, we know how to run on old CPUs. We know how we're going to make this stuff run on new stuff. When the more and more specialized we get, the bigger and bigger a problem that's going to become. And so I think, in a funny roundabout way, it's like I wouldn't be doing exactly this, but trying to figure out something on that direction of like, how do we create sustainable ways of dealing with dealing with hardware to try to figure out how we stem this mess, because otherwise, if we're throwing away our hardware every 2 or 3 years instead of what we're doing now, um, every everything that we're accomplishing here, even in the AI space, whatever, just becomes impossible to keep going. We're riding the backs of enormous amounts of new hardware, new build out and stuff, and if we can't figure out ways to make that last, a lot longer, um, than than just a few years, then we're just creating our own massive disaster. And I think I'd love to figure out ways to do that. I guess the other really exciting one, that I think you and I have talked about quite a bit is like elder care.
Yeah.
Obviously, like my parents, in their 80s, um, and I think there's so much loss when older people lose their independence. And I think being able to rely on, you know, kind of uh, kind of technology to help keep your independence even longer, and then deal with things where you're not kind of bothering people in the way. But that requires not just software, not just advances in AI, but in translating that, through hardware, through real world systems to something that is, sustainable, but also very adaptable, because it's not going to be operating in a nice factory. It's not going to be in an Amazon warehouse where you can make everything exactly the same. It's going to be operating in, parents' condo, this house, this whatever, in a situation with, different people and things. And I think really figuring out ways in which we can make things super adaptable to all kinds of different scenarios, all different things, I think, could really make the aging process and kind of the kind of lifestyle that we want for our parents, for ourselves, and for one day our kids. That could be just an enormous contribution. And I think, the stuff they doing at Conduit, and um, a lot of things that are just going on in this space, I think could be huge for humanity, and just making people's lives a whole lot better in the future.
I love it. That's the best place to end this conversation. The most inspiring thing I've heard all week. And yeah, like we are similar in that mission of how do we apply this stuff now to actually,
Yeah, it's a tough
there's
problem.
more than enough opportunity out there. We just need more founders and entrepreneurs and builders like yourself to focus on. So I'll make it happen. We'll start a company. You can be the CEO of it. And one day,
Someday.
Andrew, thank you so much. I know we're over time. Uh, and hopefully I'll see you this weekend or next week. Have a great trip to China. I know you're going over to Microsoft Research over there and with the gang, and say hi to the folks, Desney and the crew.
Will do.
Appreciate it, and
Always a
take
great
care.
time. Excellent. Thank you so much.
All
Have
right,
a great one,
cheers.
Hamish.